In the void between the constellations of Centaurus and Cercinus, suspended in the silent, unending darkness of interstellar space, lies a protoplanetary nebula known as the Boomerang. It is a ghost of a dying star, a vast, hourglass-shaped cloud of gas and dust expanding outward at a velocity of 164 km per second. This rapid expansion is an act of cosmic refrigeration, a process so efficient that the internal temperature of the nebula has fallen to a mere 1 Kelvin. This is colder than the faint, residual afterglow of the Big Bang, the cosmic microwave background radiation that permeates all of space and establishes a universal baseline temperature of 2725 Kelvin. For a region of the universe to be colder than the echo of its own creation is a profound anomaly, a pocket of exceptional stillness in a cosmos born of fire. It is the coldest known natural location, a place where the fundamental hum of the universe has been muted to an almost imperceptible whisper. Yet even this extraordinary cold is not the end of the journey. It is merely a signpost, a marker on a scale that descends toward an absolute, a theoretical limit where the very concept of temperature dissolves into a state of perfect quantum order. This limit, 0 on the Kelvin scale, or negative 45,967 degrees Fahrenheit, is not a place but a state of being, a destination that can be approached but never truly reached, an ultimate ground state for all matter and energy. To understand what occurs at this boundary of existence is to move from the scale of nebulae to the realm of the atom, to witness the gradual unwinding of thermal chaos into a state of bizarre and beautiful coherence, a world governed not by the familiar laws of motion, but by the subtle and inexorable rules of the quantum. Temperature, in its most fundamental sense, is a measure of motion. It is not an intrinsic property of a single particle, but rather the statistical expression of the collective, chaotic energy of a vast population of atoms or molecules. At the familiar temperatures of a terrestrial environment, this energy manifests as a relentless, invisible storm. Within a seemingly placid volume of air, molecules of nitrogen and oxygen, numbering in the trillions of trillions, hurtle through space at hundreds of meters per second, their paths a frantic, three-dimensional web of collisions and rebounds. They are not merely translating from one point to another, they are also spinning on their axes, executing furious pirouettes, and their constituent atoms are vibrating against their chemical bonds, stretching and compressing like microscopic springs. It is this combined kinetic energy, the sum of all translation, rotation, and vibration, that we perceive as heat. In a solid, such as a block of iron, the atoms are constrained within the rigid geometry of a crystal lattice, their freedom of movement curtailed. They can no longer roam, but they are far from still. Each atom oscillates furiously about its fixed position, a prisoner in a crystalline cell, its vibration a tremor that propagates through the entire structure. This atomic shivering is the solid's thermal signature. When a hotter object touches a colder one, this microscopic violence is transferred through collisions at their interface, the more energetic particles imparting some of their motion to the less energetic, until a state of thermal equilibrium is reached. The entire edifice of classical thermodynamics is built upon this statistical behavior of immense ensembles, a science of averages where the frenetic dance of the individual is smoothed into the predictable properties of the whole. To cool a substance is therefore not to remove some ethereal fluid of coldness, but to systematically rob its constituent particles of their kinetic energy, to gently but persistently calm the microscopic storm. The journey downward begins with familiar transitions, transformations of state that are macroscopically obvious yet atomically profound. As a gas is cooled, its constituent particles, once moving with unrestrained freedom, begin to lose their momentum. The average velocity of the ensemble decreases, and the wild, expansive pressure they exert on their container diminishes. The invisible tempest is calming. At a specific threshold, the attractive forces between the particles, the subtle van der Waals interactions that were previously overwhelmed by kinetic energy, begin to assert their influence. The particles start to cling together, their motion now constrained, and the gas condenses into a liquid. Within this denser state, the particles slide and tumble over one another, still dynamic but no longer independent. The freedom of translation is now limited to the confines of the liquid volume. As more energy is withdrawn, this sliding motion also becomes more sluggish, the liquid growing more viscous, its internal friction increasing. Eventually, a second threshold is crossed. The particles surrender their remaining translational and most of their rotational freedom, locking into place in a highly ordered, repeating pattern. The liquid freezes, becoming a crystalline solid. Here, within the rigid architecture of the lattice, the atoms are fixed in space, their identities defined by their position relative to their neighbors. All that remains of their former thermal fury is the vibration, a continuous, localized shuddering about their equilibrium points. This residual motion, this shiver in the crystal, is the last bastion of classical heat. From the perspective of the macroscopic world, the object is now cold, inert, and still. But at the atomic scale, it remains a place of immense, albeit constrained, activity. The journey toward absolute zero has only just begun, and the rules of the world are about to change completely. The simple, intuitive picture of tiny spheres slowing down is insufficient for what lies ahead, for the path leads directly into the heart of the quantum realm. As the temperature continues to fall, descending through the final few degrees that separate the solid state from the absolute floor of existence, the familiar landscape of classical physics recedes, giving way to a strange and counterintuitive terrain. In this ultra-cold domain, particles cease to behave like distinct, localized points and begin to reveal their more fundamental nature as waves of probability. According to quantum mechanics, every particle possesses a de Broglie wavelength, an intrinsic wave-like character whose scale is inversely proportional to its momentum. At high temperatures, the particle's momentum is large, and their corresponding wavelengths are infinitesimally small, far smaller than the particles themselves, allowing them to be treated as classical objects. But as the system is cooled, the particle's momentum decreases dramatically, and their wavelengths begin to grow. They become fuzzy, their positions and velocities no longer perfectly defined but instead described by a wave function, a mathematical object that encodes the probability of finding the particle at any given point in space. As the temperature approaches absolute zero, these wavelengths can become enormous, even larger than the average distance separating the particles. At this point, the very concept of individual, distinct particles begins to break down. Their probability waves start to overlap, to interfere with one another, and the system can no longer be described as a collection of individuals. It must be treated as a single, collective quantum state. The discrete nature of energy also becomes paramount. Unlike in the classical world, where a particle can possess any amount of energy, a quantum system can only exist in specific, quantized energy levels, like the rungs of a ladder. Cooling the system is equivalent to forcing its particles down this energy ladder, one discrete rung at a time. The smooth, continuous ramp of classical energy gives way to a staircase, and as the system approaches 0 Kelvin, its constituent particles are compelled to occupy the lowest possible rungs available to them, a process that leads to extraordinary and unprecedented forms of collective behavior. A persistent misconception holds that at absolute zero, all motion must cease entirely. This idea, born of classical intuition, envisions a universe frozen in perfect stasis, every atom locked in absolute stillness. The reality, as dictated by the laws of quantum mechanics, is far more subtle and profound. The Heisenberg uncertainty principle states a fundamental limit on the precision with which certain pairs of physical properties, such as a particle's position and its momentum, can be known simultaneously. To know a particle's momentum with perfect certainty, that is, to know that its momentum is exactly zero, would necessitate an infinite uncertainty in its position. The particle would, in effect, cease to exist at any specific location. Conversely, to pinpoint a particle's position exactly would render its momentum completely uncertain. A particle confined within a crystal lattice or an atomic trap is, by definition, localized in space. Its position is known to within the bounds of its confinement. Consequently, its momentum cannot be zero. It must possess some minimal, non-zero momentum, and therefore some minimal, non-zero kinetic energy. This irreducible, fundamental energy that a quantum system retains even at absolute zero is known as the zero-point energy. It is not thermal energy that can be removed, it is an intrinsic property of the quantum ground state, a consequence of the wave-like nature of matter and the very fabric of spacetime. It is the universe's prohibition against perfect stillness. Thus, even at 0 Kelvin, the atoms in a crystal lattice would not be motionless. They would continue to execute a subtle, ghostly vibration around their fixed positions, a fundamental quantum tremor. This is not the chaotic shudder of heat, but a coherent, synchronized oscillation of the entire system in its lowest possible energy state. Absolute zero is not a state of absolute rest, but a state of perfect quantum order, a dynamic stillness where the last vestiges of random, thermal motion have been extinguished, leaving only the indelible, unquenchable hum of quantum reality. Within this ultra-cold world, matter begins to exhibit properties that defy all classical experience. One of the most spectacular of these is superfluidity, a state observed in liquid helium, for when it is cooled below a critical temperature of 217 Kelvin, known as the lambda point. Above this temperature, helium behaves as a normal, albeit very cold, liquid. But as it crosses the threshold, it undergoes a phase transition into a new state of matter, a quantum fluid. The underlying mechanism is a phenomenon known as Bose-Einstein condensation. Helium, for atoms are bosons, a class of particles that are permitted by quantum rules to occupy the same quantum state simultaneously. As the liquid is cooled, a growing fraction of the atoms begins to fall into the lowest possible energy state, the ground state. Their individual wave functions, now swollen to macroscopic dimensions by the extreme cold, merge and overlap until the atoms lose their individuality entirely. They begin to behave as a single, coherent quantum entity, a macroscopic wave function that describes the entire volume of fluid. The most striking consequence of this quantum coherence is the complete disappearance of viscosity. A normal fluid resists flow due to internal friction, as its molecules collide and scatter off one another, dissipating energy as heat. In a superfluid, all the constituent atoms are locked into a single quantum state, moving in perfect unison. There is no internal mechanism for scattering or energy dissipation. The fluid can flow without any friction whatsoever. A superfluid placed in a rotating container will remain perfectly still. It can flow up the walls of its container in a thin film, seemingly defying gravity, driven by surface tension and its frictionless nature. It can leak through microscopic cracks, pores so small that they would be impermeable to any normal gas or liquid. A vortex in a superfluid does not behave like a whirlpool in water, its rotation is quantized, meaning it can only spin at discrete, specific speeds. Observing a superfluid is to witness the strange, probabilistic rules of the quantum world manifest on a human, visible scale, a silent, frictionless river of atoms moving as one. A parallel and equally astonishing phenomenon occurs in certain solid materials at extremely low temperatures, superconductivity. In a normal electrical conductor, such as copper wire, electrons flow through the material, but their journey is not unimpeded. They constantly collide with the vibrating atoms of the crystal lattice and with impurities, scattering and losing energy, which is dissipated as heat. This is electrical resistance. However, when a superconducting material is cooled below its specific critical temperature, this resistance abruptly vanishes. It does not just become very small, it becomes precisely zero. An electrical current induced in a superconducting loop will, in theory, flow forever without any loss of energy, a persistent current that constitutes a form of perpetual motion machine. The quantum mechanical explanation for this effect is rooted in the behavior of electrons within the cold crystal lattice. Electrons are fermions, particles that cannot occupy the same quantum state. However, as they move through the lattice, a subtle interaction occurs. An electron slightly distorts the lattice of positive ions around it, creating a region of concentrated positive charge. This region then attracts a second electron. This indirect attraction allows two electrons to bind together into a loosely associated pair, known as a Cooper pair. This pair of fermions now behaves, in a collective sense, like a single boson. Just as the helium atoms in a superfluid can condense into a single ground state, these Cooper pairs can also condense into a coherent, macroscopic quantum state that spans the entire material. In this state, the pairs move in unison, their wave functions locked in phase. They flow through the crystal lattice as a single entity, a superfluid of charge. An individual Cooper pair cannot easily be scattered by a lattice vibration or an impurity without breaking the pair apart and disrupting the coherence of the entire condensate, an event which is energetically unfavorable. The flow of charge is therefore protected by this collective quantum state, resulting in zero electrical resistance. Superconductors also exhibit the Meissner effect, the active expulsion of all magnetic fields from their interior, a property that allows for dramatic feats of quantum levitation, where a magnet can be made to float effortlessly above a superconductor, suspended by an invisible, frictionless quantum force. The ultimate expression of quantum coherence at low temperatures is the creation of a pure Bose-Einstein condensate, BEC. While superfluid helium represents a partial condensation in a dense liquid, a true BEC involves cooling a dilute gas of bosonic atoms to temperatures far lower still, typically in the range of nanokelvins, billionths of a degree above absolute zero. Achieving such temperatures requires a sophisticated sequence of laser cooling and magnetic trapping. First, atoms are bombarded with laser light from all directions. The lasers are tuned to a frequency slightly below the atom's resonant frequency, so that they preferentially absorb photons when moving toward a laser beam, slowing them down due to the Doppler effect. This process, known as an optical molasses, can cool the atomic gas to microkelvin temperatures. The pre-cooled atoms are then transferred to a magnetic trap, a carefully shaped magnetic field that confines them in a small volume. The final stage of cooling, evaporative cooling, then begins. The magnetic trap is gradually weakened, allowing the most energetic, hottest, atoms to escape, just as steam escapes from a cup of hot coffee. Each escaping atom carries away a disproportionate amount of energy, lowering the average kinetic energy, and thus the temperature, of the remaining population. As the gas is cooled through the final nanokelvin thresholds, a dramatic phase transition occurs. A sharp peak appears in the velocity distribution of the atoms, indicating that a significant fraction of them have suddenly collapsed into the single lowest energy quantum state of the trap. They are no longer a gas of individual particles, they have become a single quantum object, a superatom, comprised of thousands or millions of atoms all occupying the exact same wave function. They are spatially co-located, moving in perfect lockstep, with all the properties of a single, massive particle. This state of matter is incredibly fragile, a gossamer-thin cloud of coherent atoms that can be studied only for brief moments before it dissipates. A Beck is the closest that matter comes to the idealized ground state, a physical realization of a quantum mechanical wave function made visible, a whisper of the perfect order that reigns in the silent world near absolute zero. The journey toward absolute zero, however, is one with a destination that can never be reached. This is not a limitation of technology, but a fundamental law of nature, codified as the third law of thermodynamics. The law states that it is impossible to reduce the temperature of any system to absolute zero in a finite number of steps. The reasoning is tied to the concept of entropy, a measure of the disorder or randomness in a system. As a system is cooled, its entropy decreases, because its constituent particles become more ordered, occupying fewer and fewer available energy states. At absolute zero, a perfectly crystalline substance would theoretically have zero entropy, as all its particles would be in the single, perfectly ordered ground state. The third law implies that the entropy of a system approaches a constant value as its temperature approaches absolute zero. A practical consequence of this is that as a system gets colder, it becomes exponentially more difficult to remove the remaining heat. Each step in a cooling process removes a certain amount of entropy. As the temperature drops, the amount of energy corresponding to that quantum of entropy also drops. To cool from 3 Kelvin to 1 Kelvin is far easier than to cool from 1 millikelvin to 1 microkelvin, which is in turn vastly easier than cooling from 1 microkelvin to 1 nanokelvin. The amount of work required to extract each successive unit of heat energy approaches infinity as the temperature approaches zero. The process is asymptotic, one can get arbitrarily close, but the final state remains infinitely far away. It is a cosmic speed limit, a fundamental barrier built into the mathematical structure of the universe. Absolute zero exists as a perfect, theoretical baseline on the cosmic thermometer, a reference point of ultimate stillness and order, but it remains an inaccessible pole, a point on the map of reality that can be navigated toward but never landed upon. The universe permits the approach to perfection, but forbids its attainment. Returning, then, to the vast, cold expanse of the cosmos, the journey into the quantum depths of temperature provides a new lens through which to view the universe. The Boomerang Nebula, at 1 Kelvin, is not a place where quantum coherence reigns. It is simply a region of classical gas that has become exceptionally cold through rapid expansion. Its atoms are still behaving as individuals, their motion greatly reduced but still fundamentally random and thermal. It is cold, but it is a classical cold. The true ground state, the world of superfluids and Bose-Einstein condensates, exists only in the most meticulously controlled laboratory environments on Earth, tiny, fleeting pockets of extreme order carved out of a universe that is, on average, far warmer. The cosmic microwave background, the 27 Kelvin echo of the Big Bang, represents the universe's current thermal state, a bath of ancient photons that sets the temperature floor for any object not actively being cooled or shielded. Yet, this too is a transient state in the grand sweep of cosmic time. The universe is still expanding, and as it expands, this background radiation will continue to cool, its wavelength stretched further and further. Over timescales of trillions of years, in a scenario known as the Big Freeze or heat death of the universe, all stars will have exhausted their fuel and winked out. Black holes themselves will have evaporated through Hawking radiation. The universe will become a vastly expanded, dark, and unimaginably cold place. The background temperature will fall asymptotically toward absolute zero. In this distant, final epoch, the cosmos itself will approach the state that is now only achievable in our laboratories. The universe will become a diffuse, near-empty void, its remaining elementary particles separated by immense distances, their kinetic energies dwindling to almost nothing. It will be a universe in its ultimate ground state, a state of maximum entropy and minimum available energy, a silent, vast, and enduring equilibrium. The frantic, hot beginning will have resolved into a quiet, cold end, a final state not of perfect quantum coherence, but of ultimate, desolate stillness, a final, faint echo of the quantum tremor that can never be completely silenced.